In section 7.6, we'll derive the double and half-angle formulas for trig functions. These formulas are essential for success in calculus. So let's go. In this section, we'll develop the double and half-angle formulas for the trig functions. So let's start with the double angle formulas for the double angle formula for sine. So we want to know if there is an easier way to write sine of 2 theta, but in terms of just theta itself. And the answer is yes. So what we can do here is we can say that 2 theta is really just theta plus theta. And now we have the sum formula. So I'm going to let alpha be the first theta and beta be the second theta. And so that would be the sine of what should be the alpha, so that's theta, times the cosine of the beta, that's theta, plus the cosine of alpha, but that's theta, times the sine of beta, which is theta. Now these two expressions are exactly the same even though they're written in different orders. So really what we have is 2 sine theta cosine theta. And that's the double angle formula for sine. So hold on to that. Let's take a look at the double angle formula for cosine. So cosine of 2 theta, we'll pull the same trick on this, is going to be the cosine of theta plus theta. So we have an alpha and a beta. And so this is going to be the cosine of alpha, which is theta, times the cosine of beta, it's theta, minus the sine of alpha, but that's theta, times the sine of beta, but that is theta as well. So this simplifies to cosine squared theta minus sine squared theta. And that's one of the double angle formulas for cosine. Turns out we can use this and the Pythagorean identities to produce 2 more. So let's go ahead and produce another version of this. In this case, what I want to do is sub out the cosine squared of theta. Cosine squared of theta is equal to 1 minus sine squared theta using the Pythagorean identity. Now we have 1 minus sine squared theta minus sine squared theta. I can combine the sine squareds theta and get 1 minus 2 sine squared theta. That's another one. Or we can take the original one here and sub out sine squared with the Pythagorean identity. And that produces cosine squared theta minus, parentheses, 1 minus cosine squared theta. Distributing the negative gives me cosine squared theta minus 1 plus cosine squared theta. And that's equal to 2 cosine squared theta minus 1. And that's the other one. So these are the 3 formulas that you can use for cosine of 2 theta. Let's look at some examples. Example 3. If cosine theta is equal to negative 4/5 and theta is between pi over 2 and pi, find cosine of 2 theta and sine of 2 theta. Well, the first one we want to use here or find is cosine of 2 theta. To find the cosine of 2 theta, I have 3 different formulas I can use. The formula to choose to use in this case is based on the pieces of information that I already have. Since I already have this cosine information here, I might as well just go ahead and use the formula that involves only the cosine of theta. So I'm going to use the formula that is 2 cosine squared theta minus 1. We know that the cosine of theta is negative 4/5, and then that has to be squared, minus 1. We have to square first, order of operations. So that would be 16 over 25. The 2 only multiplies into the numerator. So we get 32 over 25 minus 1. And then 32 over 25 minus 1. Here's a little trick that you can use. Multiply 25 times 1 and then subtract that from 32. So basically 32 minus 25 is 7. So the cosine of 2 theta is 7/25. Next, let's find the sine of 2 theta. Now this is much easier to handle because there's only one formula. It is 2 sine theta times cosine theta. We have 2. We need the sine of theta. We don't have that yet. We'll have to figure that out. The cosine of theta is negative 4/5. To find the sine of theta, we need a theta circle. We know that theta is in quadrant 2. And so draw that over here. We know that the cosine of theta is negative 4/5. So negative 4 is the x, 5 is the radius, and that makes 3 the y value using a 3, 4, 5 triangle. Therefore, the sine of theta is 3 over 5. The y over the r. And then multiply these together, and you get negative 24 over 25. Example 4. Use the double angle formula to expand sine of 6 theta. So if I want to use the double angle formula, first let me write the problem, sine of 6 theta. To use the double angle formula, I have to figure out what angle is actually being doubled here. So this is going to be the sine of 2 times some angle. Well, 6 theta is 2 times what? And the answer is 3 theta. So now 3 theta is going to be used in the double angle formula. So that means the expansion is 2 times the sine of 3 theta times the cosine of 3 theta. So this is very positional. The 3 theta was what is being doubled, so it goes in the angle argument here for sine and cosine. Example 5. Derive the formula for tangent of 2 theta. Tangent of 2 theta would be the tangent of theta plus theta, and these are the alpha and the beta again from the previous stuff. And then we use the sum formula for tangent. So that's going to be tangent of theta plus tangent of the other theta divided by 1 minus tangent of theta, the first one, times tangent of theta, the second one. And then this simplifies. So the tangents on top add together. We get 2 tangent of theta divided by 1 minus, and the 2 tangents on the bottom multiply. And that becomes tangent squared theta. And that's the double angle formula for tangent. Example 6. If tangent theta is equal to 1/2, find tangent of 2 theta. So tangent of 2 theta is equal to 2 tangent theta over 1 minus tangent squared theta. That's equal to 2 times, the tangent of theta is 1/2. So we'll plug that into both versions here. The denominator becomes 1 minus 1/2 squared. Let's work that out a little bit. 2 times 1/2 is just 1. The bottom is 1 minus 1/2 squared is 1/4. So now I have a compound fraction. Let me multiply both the top and the bottom by 1 in the version of 4 over 4. That is going to distribute to the top and distribute through the bottom here. And that's going to give me 4 over 4 minus 1, which is 4/3. Next, let's develop the half-angle formulas. So let's start with one of these cosine double angle formulas here. The cosine of 2 theta is equal to 1 minus 2 times sine squared theta. And what I want to do is I basically want to solve this for sine squared. So this is going to be, let me move the 2 sine squared to the left. So we get 2 sine squared theta. That is going to be equal to 1, and then move the cosine to the right, minus cosine of 2 theta. And then I'm going to divide both sides by 2. So we're going to get sine squared theta is equal to 1 minus cosine of 2 theta over 2. And this is how we're going to think about the half-angle formula in this case. And the reason this works is because the angle theta that is sitting right here is half of the angle that's sitting inside the cosine. Even though it's represented as theta and then 2 theta, we still have sort of the half relationship. Now I'll go ahead and tell you the way some other people do this. They go ahead and use alpha or maybe something else, but they say sine squared of alpha over 2. So they already have the half angle, just like we had a double angle, we had 2 theta. We have a half angle, it's half of alpha. And then that this is equal to 1 minus cosine of alpha over 2. We still have this relationship that is a half among the angles. We're going to try to focus on the ones on the left side here for this class. Similarly, you can develop the other formulas for cosine and tangent. We'll go ahead and give those to you here. So the cosine squared of theta is equal to 1 plus the cosine of 2 theta over 2. And the tangent squared of theta is equal to 1 minus cosine of 2 theta over 1 plus cosine of 2 theta. There are other versions of these, and especially the half-angle formula for tangent. There are multiple versions of that that don't even look like the one that's presented here. You may see those on the formula sheet. You're welcome to use them if they come in handy. Now, how do we use these formulas? Let's look at example 7. Find the exact value of sine of 15. So I'm going to use the formula we developed above, and we're going to start with sine squared of 15. So ultimately, we will have to take a square root. We'll get to that in a moment. But sine squared of 15 is equal to 1 minus cosine of 2 times the angle, 15 degrees, over 2. And notice that relationship right there, 15 and 15, and then this angle is going to become twice of 15, meaning that the 15 on the left is half of the angle that you actually use in the formula. That's why it's called the half-angle formula. This is 1 minus cosine of 30 degrees over 2. Cosine of 30 is root 3 over 2 by 2. Let's clear out denominators by multiplying by 2 over 2. The 2 distributes. That's going to give me 2 minus root 3 over 4. But that's not quite the answer, because remember that that is sine squared of 15 degrees. So we do need to take a square root. Now the question is, when I take the square root, should it be positive or should it be negative? And the answer lies in the angle itself. 15 degrees is in quadrant 1. And the sine of 15 degrees should then therefore be positive. So the sine of 15 degrees is going to be the square root of this number we have here, 2 minus root 3 over 4. And in this square root covers everything, the entire fraction. We're going to use the positive on this because we're in quadrant 1. Had we been in quadrant 3 or quadrant 4, then sine would be negative, and we use the negative. One more simplification, split the square root up over the numerator and the denominator, and the square root of 4 is 2. So the sine of 15 degrees is root 2 minus root 3, and this root 3 is inside the square root with the root 2 there, with the 2, and then all that divided by 2. Example 8. If sine of alpha is equal to negative 5 over 13, and alpha is in quadrant 3, find the sine of alpha over 2, cosine of alpha over 2, and tangent of alpha over 2. So we're being asked for the half angles of these three trigonometric functions. The first thing we want to do is figure out which quadrant alpha over 2 is in. It tells us that alpha is in quadrant 3, but it doesn't tell us where alpha over 2 is, and we have to figure that out. So first, let's draw the alpha circle in general. And what we know is that alpha is in quadrant 3. So alpha is somewhere down here in quadrant 3. The bounds on alpha, therefore, are between pi and 3 pi over 2. So alpha is between pi and 3 pi over 2. Now to figure out where alpha over 2 is, we're going to multiply everything by a half. And so the middle is alpha over 2, the number we want. The left side becomes pi over 2, so right here. And the upper bound becomes 3 pi over 4, which is halfway in quadrant 2. So we know that alpha over 2 is in quadrant 2. It doesn't have the possibility of being anywhere in quadrant 2. It has to be between pi over 2 and 3 pi over 4, but that's enough at least to tell us what quadrant it is in, and therefore what signs we have to use when we go to compute the sine of alpha over 2 and the others. So we know that we have a quadrant 2 angle. Since the sine of alpha was negative 5 over 13, that means the y is negative 5, the radius is 13, and if you remember this Pythagorean triple, you'll remember that the x is 12, but since it's in the quadrant 3, It's negative 12. And this is the angle alpha. Now we use the alpha circle to give us the information about alpha over 2. So let's go with our identities here. So sine squared of alpha over 2 is equal to 1 minus the cosine of alpha over 2. Notice how we're going to still use information about alpha in this problem. That's why we have the alpha circle. So this is going to be 1 minus, well, the cosine of alpha is the x over the radius, r. So it's negative 12 over 13 divided by 2. Let's go ahead and simplify this by multiplying the top and the bottom by the little denominator of 13. The 13 distributes, gives me 13. We have double negative, that turns into plus. 12 over 13 times 13 is 12, divided by 2 times 13 is 26. 13 and 12 is 25 over 26. Now this is still equal to sine squared of alpha over 2. To solve for sine of alpha over 2, we take the square root. So we're going to have sine of alpha over 2 is equal to the square root of 25 over 26. That splits up to be the square root of 25 over the square root of 26, which is going to be 5 over root 26. And then you can rationalize by multiplying top and bottom by square root of 26. So we get 5 root 26 over 26. Now, is this positive or negative? Well, alpha over 2 is in quadrant 2. And in quadrant 2, the sine of an angle in quadrant 2 is positive. So it is positive 5 root 26 over 26. Next, let's do the same thing with cosine. So we'll have cosine squared of alpha over 2 is equal to 1 plus cosine alpha over 2. The cosine of alpha, again, is negative 12 over 13 divided by 2. Go ahead and simplify this fraction by multiplying by 13 over 13. And we get 13 minus 12 over 26. This is equal to 1 over 26. We still have cosine squared of alpha over 2, so I need to take the square root of both sides. The square root is going to be the square root of 1 over 26. Alpha over 2 is a quadrant 2 angle, and the cosine of a quadrant 2 angle is negative. So let's go ahead and make this negative, and then continue to simplify. Becomes negative square root of 1 over the square root of 26. That's equal to negative 1 over root 26. And then rationalizing, we get negative root 26 over 26. Finally, let's go for tangent of alpha over 2. You can use one of the formulas if you'd like to do that, or you can just recognize that this is the sine of alpha over 2 divided by the cosine of alpha over 2. And that would be 5 root 26 over 26 divided by negative root 26 over 26. The 26's in the little denominators cancel. The root 26's in the numerators of the little fractions cancel. And we're left with a 5 and a -1 in the bottom. 5 divided by -1 is -5. Example 9. Solve the equation. Sine of 2 theta times cosine of 2 theta is equal to 1/2 for theta between 0 and 2 pi. So we want to solve this. Let me rewrite the problem here. Sine of 2 theta, cosine of 2 theta is equal to 1/2. Well, it's very difficult to solve because we have two different trig functions here. If there's some way I could alter this so that I could condense these down into one trig function, then that would really help. And the trick is to recognize that this is almost the double angle formula for sine. Now, it doesn't quite go the way you would think. You see the 2 theta, that's actually not the way we want to go. Remember that the double angle formula for sine is 2 sine theta cosine theta. And I have the sine and cosine parts already there. What I need to do is bring in a 2 so that now the left side looks like the double angle formula, not of 2 theta, but of 4 theta. So the sine of 4 theta is the sine, 2 times the sine of 2 theta times the cosine of 2 theta. But I can't just arbitrarily start multiplying by 2's. I have to multiply by 2 on both sides. And now we're in business. So the left side condenses down to the sine of 4 theta is equal to 1. And this is a problem from several sections ago. We're looking for the angles where sine is equal to 1. That only occurs at one spot on the unit circle, and that is pi over 2. But because of the 4 in the 4 theta, we have to extend this out 4 periods. So adding 2 pi repeatedly is going to give me 5 pi over 2, 9 pi over 2, and 13 pi over 2. And finally, solving for theta by multiplying everything by a fourth, we get pi over 8, 5 pi over 8, 9 pi over 8, and 13 pi over 8. Let's look at example 10. Solve the equation. Sine of theta plus cosine theta equals 1 for theta between 0 and 2 pi. Again, we have multiple trig functions. There doesn't seem to be an obvious substitution that we can use here. The sine and the cosine are not squared, so the Pythagorean identity doesn't work. They're not really reciprocals of each other. There's no exotic trig functions like cosecant or anything. So we need to use a technique that we sort of reserved for emergency cases. And that is to take both sides of this equation and square it. When we square it, we need to use FOIL and multiply out the left side. When you do, you get sine squared of theta plus 2 sine theta cosine theta plus cosine squared theta is equal to 1. Don't forget the middle term. Next, sine squared theta plus cosine squared theta is the Pythagorean identity. That simplifies to 1. That leaves us with 1 plus 2 sine theta cosine theta equals 1. 1's cancel. That leaves us with 2 sine theta cosine theta equals 0. Now we're stuck like we were in the last problem, but I think this one is a little more obvious to see. We have the double angle formula for sine. So let's condense this back down. To sine of 2 theta is equal to 0. Solve this for when sine is equal to 0. That means zeros for the y-coordinates. And that happens at 0 and pi. But because of the 2, I need 2 periods. So we have 2 pi and 3 pi added onto that. And then divide by 2. So we get theta is equal to 0, pi over 2, pi, and 3 pi over 2. But wait, we have to remember that we squared the original equation. And when you do that, you run the risk of bringing in what they call extraneous roots. Extraneous roots are extra roots that match the new equation that you found after squaring, but do not satisfy the original equation as it was. So we have to check all of these. And I guess I'll just do it right over here. So if theta is equal to 0, the original equation would say that the sine of 0 plus the cosine of 0 might be equal to 1. Sine of 0 is 0, cosine of 0 is 1, and that's 1 equals 1, so that works out. For theta equals pi over 2, we would have sine of pi over 2 plus cosine of pi over 2 might be equal to 1. Well, the sine of pi over 2 is 1. The cosine of pi over 2 is 0. And 1 plus 0 is 1. That's equal to 1. That one checks out as well. So far, so good. Next, let's check when theta is equal to pi. The equation would be sine of pi plus the cosine of pi might be equal to 1. The sine of pi is 0. The cosine of pi is negative 1. And this is negative 1 is equal to 1. That one is not true. This one does not work. So we have to get rid of theta equals pi. And I'll just move this one over to here. Checking the last one, we get the sine of 3 pi over 2 plus the cosine of 3 pi over 2 might be equal to 1. But the sine of 3 pi over 2 is negative 1, the cosine of 0, and that's going to be bad. Negative 1 is not equal to 1, so this one is gone as well. So out of all of these, we only had 2 valid solutions, and the other 2 had to be tossed because they were extraneous. Example 11. Establish the identity. Cosine of 2 theta over 1 plus sine of 2 theta is equal to cotangent theta minus 1 over cotangent theta plus 1. So let's establish the identity. Start with the left side. And the first thing I notice in particular about this problem is that there are 2 thetas on the left side, the trig function of 2 theta, but on the right side it's only regular 1 theta. So we do need to use the double angle identities to work this out to produce the single thetas. So the first thing we'll do is change both the cosine of 2 theta and the sine of 2 theta using the double angle formulas. So the top one, cosine of 2 theta, is going to be cosine squared theta minus sine squared theta over 1 plus the sine of 2 theta is 2 sine theta cosine theta. Next, let's factor the top. We have the difference of 2 squares. So this is going to be cosine theta minus sine theta and cosine theta plus sine theta. And the bottom, this one is a little tricky. We're going to take this 1 right here, and we are going to re-expand it back into cosine squared theta plus sine squared theta. So this is going to be cosine squared theta plus the piece that we already had, 2 sine theta cosine theta, plus the rest of this. And I wrote it in this order so you could see how it's going to factor. It's going to factor really nicely here. But that's where the 1 went. The 1 became cosine squared plus sine squared. All right, let's go ahead and factor the bottom. The top stays the same. And the bottom is a perfect square, so it's cosine theta plus sine theta quantity squared. With this, cosine theta plus sine theta on the top cancels with one of the factors of cosine theta plus sine theta on the bottom. That leaves us with cosine theta minus sine theta over cosine theta plus sine theta. And at this point, you can see that it looks very much like what we want. It's not quite there yet. So now the question is what to do. Well, I really want to get cotangent in this first position, and I really want to get a 1 in this second position. So what I need to do is somehow divide by the sine that's in this right position. And that'll work really well. So I'm going to multiply by 1 over sine theta over 1 over sine theta. So I'm multiplying by 1, but it's in the form of 1 over sine theta over itself. This will now distribute to both pieces here. And we get cosine theta over sine theta minus sine theta over sine theta divided by cosine theta over sine theta plus sine theta over sine theta but cosine theta over sine theta is cotangent theta. Sine over sine is 1, and cotangent theta plus 1 in the bottom. And that's that.